All right, so I think we can start the preliminary presentations for today. And as last week, each group will have 7 minutes for your talk and 3 minutes for Q&A. And to reduce the number of interruption, I'll try to remind you over the text chat for the Google Meet first. Unless you really go over time, then I will speak up. All right. So I think we can go ahead and start with the presentation for Group 6 from Mr. Chen Pinghan and Ye Baixiang. Will one of you start to share your screen and go ahead?
Okay. Can everyone hear me?
Yes, I can hear you.
Let me share my screen. Okay, now is my PowerPoint on the screen?
Yes.
Okay. Hello, everyone. We are Group 6. I am Pinghan Chen. Today, me and my partner, Baixiang, gonna introduce the 2D Ising model and how to analyze it by machine learning method. And there is our outline. Our logic flow is to try to analyze an unknown data set with physics viewpoint. Therefore, we follow the guideline from teacher. Start with the data description and try to give a physics explanation, and then simply introduce what is Ising model. In the end, how we want to analyze it by machine learning method, including what feature we want to use. First, we know that our data includes 3 parts: spin data, label, and parameter. In order to get the what information contained in X, we also print it out and find what it is stand for the pixel information for an image. Therefore, we plot those data and get a figure with the dependent to the temperature. We can observe that as the increasing of the temperature, the spin is getting messy. This is obviously like the order-disorder phase transition in statistic physics. As the figure shows, in low temperature, the magnetization has a certain direction. When the temperature increases, the magnetization disappears. This spin system on the lattice is so-called the 2D Ising model. 2D Ising model is a system where spins have 2 directions, up and down, located on the square lattice, shows on the left of the screen, which means each side has 4 neighbors with the spin-spin coupling, where our Hamiltonian for this system is minus j times sum over SI And the reason of the phase transition is when we look at the free energy of the system. We know that the energy is from the spin-spin coupling and with the energy strength J, and the entropy comes from how messy the current spin configuration is. And due to the system tend to minimize the free energy, therefore, for the low temperature region, the energy part dominates. For the high temperature region, the entropy part dominates, which in the end turn to be the order and disorder phase. And the transition is so-called the order-disorder phase transition. And Baixiang will introduce the figure explanation for us.
Can everyone hear me?
Yes.
And now I'm going to talk about the features in the Ising model. And besides the low-level feature, which is the spin configuration we just mentioned, there are some high-level features such as energy, heat capacity, magnetization, susceptibility, entropy, and free energy, we can calculate from the raw data. The formula used to calculate these features and the figures for them are shown in the slide. We can see that for heat capacity and susceptibility, there is a sharp peak at the critical point. For the other features, the change before and after the critical temperature is not dramatic, but we can still find some difference. Next page. One another useful feature is the distribution of magnetization. From the left figure, I show the distribution of absolute magnetization for some specified temperature. And we can find that the distributions are different for each temperature. The right figure shows the distribution near critical temperature. The distribution at temperature 2.28 is quite different from the distribution at temperature 2.48. The difference between them is sufficient to be used to implement the classification. Next page. The proposal of our machine learning can be divided into three parts. First is the classification by using low and high level feature. Since the low level feature is spin configuration, which is two-dimensional data, it would be better to use deep neural network as the model, while a linear discriminator is suitable for the one-dimensional high-level features. The second one is the regression. We can try to predict the temperature from both low-level and high-level features, although this is not quite related to the phase transition of easy model. And the last one is the generative model. We can take temperature and some random noise as the input and generate the fake data from the generator. The discriminator distinguishes fake data from the real spin configuration dataset. After training, the generative model can be used to generate some spin configuration dataset instead of using the Metropolis algorithm of Monte Carlo method. Next page. And this is our reference. Thank you for your attention.
Thanks. It's right on time. Great. Any questions or comments for group 6? So if not, I have a naive question for this study. So one of your tasks is classification, right? So I guess you mean if you feed say a spin configuration and you want to classify whether it's say paramagnetic phase or ferromagnetic phase. I mean, that's the goal of your classification task, right?
Yes.
Okay, I'm just wondering, will that be trivial since you already know the transition temperature and basically the parameter of this model?
Sorry, I have not quite understand what your question
sorry,
is.
I'm just saying that will that be trivial since your transition temperature of the parameter of transition temperature of this this easy model.
Yes.
I'm just wondering how I'm just curious if things like DNA will be too overkill for this classification task. But anyway, I'm just but this is like I understand this is a simple model, so so it could be so sometimes some aspect could be very trivial. But anyway, I just want to make sure what's the goal of your classification task. Okay. All right. Any other questions or comments?
Yeah, I want to ask your high-level feature definition. Can you help me to understand how do you calculate the E square?
You mean this page?
Yes. How do you calculate E square? Because your capacitance C is E square average minus E average square. So how do you calculate E square?
Yes. Okay. So, do you want to let us show our code, or just simply tells you?
Yeah, just explain the formula to me. How do you calculate E square average?
Okay, because this average stands for the ensemble average, means because our data has 100 ensemble. Therefore, we just square the all the total energy and then calculate the square after the ensemble average. Is that clear or?
I don't understand your explanation. Yeah. So I can see a clear formula. How do you define the E average? It's the sum of the SI times SJ, right? So how do you calculate E square average?
We can simply calculate the ensemble average of the energy, and for the energy which
So what's the formula?
Square before the ensemble, we just calculate the energy of each configuration.
Yeah. So what's the formula?
And then
Can you just explain the formula to me? Yeah.
Explain the formula to you.
Yeah. So you have a clear definition. The E, right? Average is sum over SI SJ. Sum over SI times SJ. So what's the E square average?
E square average.
Maybe I can answer the question. And for each configuration, we can calculate the energy by the formula in the slide, and we just square this energy. It means the square E of this configuration. And since for one temperature, we have 100 configurations, so we just take the average.
So if you write out the formula, how the formula look like?
We didn't write it in the slide.
I know, but can you just read? If you are going to write the equation, how the equation looks like?
It just is the sum, the square of sum of SI SJ for each nearest neighbor.
You mean the square is outside the sum or inside the sum?
Outside the sum.
I don't understand your formula. Yeah, this is my question here. Hopefully you can write out the equations and then we can learn in your final report.
Okay.
We will write in the final report.
I'm talking about E square average, not E average square. I'm asking E square average, not E average square. Yeah. Do you understand the difference between the two? Look at your C definition.
So,
there are two terms. One is E square average. The other is E average square. Okay.
Well, there's a problem in our slides. The formula is wrong, since the formula of some SISJ is not the average of energy. It should be directly the energy of one configuration. So we still need to sum over all configuration and take the average.
Okay, so you are saying there's a mistake in your slide and you need to rewrite the equation. Okay, all right.
Yes.
All Hi, thanks. So if no further question or comments, let's then we can move on. Thanks, Group 6, and we can move on to Group 7, Miss Wu Meijie and Miss Wu Xingyu. So one of you could start sharing and go ahead.
I'll share my screen.
Okay.
And can everyone see my screen?
Yes.
Okay. And hello everyone, we are Group 7 and today's topic is machine learning on Higgs production. I'm Wu Xingyu and my partner is Wu Wenjie. This is today's outline. The presentation will contain physics behind data, data description, feature exploration, and the proposal of machine learning study. First, I'll introduce physics behind data. The Higgs boson was discovered at the LHC in 2012 and the study of its properties has just begun. They are produced from 4 different modes, as figures show. Since it was discovered, we have to find the technique to distinguish them. A major motivation for the study of boosting H2BB final state in particular is that it allows us to study the structure of the GG to H process at high PT. However, it has other processes, including BBF, VH, and TTH. So GGF means the two gluons combine to form a loop of virtual quarks. And in the VH part, if an elementary fermion collides with an antifermion, the two can merge to form a virtual W over Z boson and then emit a Higgs boson. BBF is that when two fermions collide and the two exchange a virtual W over Z boson which emits a Higgs boson. And finally, TTH involves two colliding gluons which each decay into a heavy quark-antiquark pair. A quark and antiquark from each pair can combine to form a Higgs particle. So if GG to H could be clearly separated from the other Higgs production modes, the sensitivity to BSM would be enhanced. And there are 4 Higgs production channels and they all Higgs to BB quark. Thus, we can distinguish them by having a look at BB, so we put focus on non-Higgs jets, which are circled in the figure. Using the data like momentum, angle of particle relative to beam axis, or using image, we can classify different modes. And next is our data description. We have 3 major groups of data, which are low-level feature, high-level feature, and data project. The low-level feature is a more primitive physical quantity that contains the momentum, the direction of particle motion. Then the high-level feature is obtained by taking the low-level feature and doing the calculation. And the third part of data is leading non-Higgs jet image. Image shows the eta and phi of jet. And next part is my partner.
Okay, can everyone see it?
Yes. You can speak a little bit louder.
Is it okay?
Yeah, it's much better. Thanks.
Okay. Here is our low-level feature data, which have 6 features. PT is high transverse momentum. The transverse momentum spectra are very important because they can provide essential information in this collision. eta is pseudo-repeated. It describe the direction of particle motion and the angle of the incident particle beam. And phi is azimuth angle is an angular measurement in a spherical coordinate system. And the data will be labeled by 0, 1, 2, 3. When we look at a low-level feature, we can find they are difficult to identify each label, except for TTH, which has a different distribution on feature real eta and real phi. Other three projection modes are very consistent, and only the number of data are different. So maybe that is why we make high-level feature, because low-level feature are not enough to describe each projection mode. Here, use 1 hot for each production mode. And this data have 12 features. High-level features are calculated based on the jet mass, jet shooter replicate, and open angle between two leading jets, the mass of the two jets, and the angle information of the jet shape. We can observe that the distribution range of some feature can be distinguished into different categories. So maybe we can use decision tree to identify each projection mode. And for data project, we can see there are a lot of jet image on the data set, and also they are already be labeled, so we can separate them. But we are not quite sure how this data set should be analyzed. However, the average of all jet image show that the VH and TTH are most spatial, so maybe we can start here to analyze them. In this part, we will explain the machine learning classifier we use to classify the 4 Higgs projection mode. First, we try to use CNN to deal with non-Higgs jet image because we think that CNN has the highest accuracy amongst most predict image. As the high-level feature and low-level feature, after data exploration, we observe the low-level feature distribution is more consistent except for HGG. So it is not very good to distinguish each type by its sig feature. So we try to use DNN to do the analysis. It is because that we think DNN can consider the relationship between multiple features in a more comprehensive way. So we choose the DNN model to try it. Finally, for high-level feature, since we can see some difference in their features, so we maybe can use decision tree to analyze it, and also we will try DNN too. Now we are doing DNN and decision tree for high-level feature and low-level feature, but we haven't success yet. And this is our reference. And thank you for your listen.
Okay, thanks. Any questions or comments?
Can you compute high-level feature from low-level feature?
Can you say it again? You mean?
Can you compute high-level feature from low-level feature?
I think is yes.
I cannot hear you. What's your answer?
Yeah, I think is yes.
And do you know the formula to how to compute those high-level feature from low-level feature?
This part I'm not sure about.
Can you figure it out and share with us in the final report?
I said I'm not sure this part because I only know the low-level.
Yes, and I asked, can you figure it out and present to us in the final report?
Okay.
Great. My next question is, do you know how to build the jet image from low-level feature?
No, we don't know.
Can you figure it out and present to us in the final report?
Okay.
Given these two questions, I believe you start understanding low-level feature is a basic. You can use a low-level feature to calculate high-level feature. You can use the low-level feature to produce jet image.
Okay.
So it's all original from low-level feature.
Okay, we will try it.
Well, I'm just asking to understand how this is done. Yeah, it'd be nice you can understand it and explain to us in the final report. Just like the previous talk, you can see it's a 2D IC model. You have a spinner in this 2D array. And from the spinner, you can calculate high-level feature, okay? You can build high-level feature from low-level feature. And it's the same as your data. Your data has a low-level feature, and you can use that to calculate a high-level feature. You can use that to build the jet image. The good thing is that already they, when Alan prepared the data, Alan already calculate those low-level feature, high-level feature for you. So you can just use it. But my goal here is that you can try to understand how does Adam calculate high-level feature from low-level feature? How does Adam create a jet image from those low-level feature?
Okay.
And it's a general assignment for the 2 HIS group. Yeah. So 4 of you can try to discuss together. Maybe one group talk about how the high-level feature are calculated from low-level feature. The other group can talk about how the jet image was built from the low-level feature. So 4 of you can try to talk to each other.
Okay, we will do that.
Okay, thanks. So we can move on to the next group, Mr. Guo Junxian and Mr. Zhang Chenyu. Again, like one of you can share your screen and go ahead.
Can everyone hear me?
Yes.
Hey. Okay, hello everyone. My name is Junxian Guo, and my partner is Zhang Chenyu. And our topic is charge particle tracking. And I'll briefly introduce the physics. The data we acquire is from the particle accelerator, which is the particle hits on the detector, and we collect the position and momentum from the detector. And we need to track the trajectory of the particles to explore the unknown particles we display in the detector. And this is the cylindrical coordinate in the detector. And we can see there is different volumes of the detector. And as the left-hand side picture, we can see different volume number in 7, 8, 9, 12, 13, 14. And our data is in the volume 8, which is the center one. And left-hand side is our data shown in the X, Y, and YZ distribution. And here is our data. Our data is 2 kinds. One is preselection data. The other is pairs. The pairs data is from preselection data, which is built from a particle from former layer to latest layer. So it becomes a pair, and if the particle ID is in the former layer is same to the last layer, it will becomes the truth, or other it will become the false. So the preselection data, we have heat ID, XYZ, volume ID, layer ID, module ID. This is the detector position and the heat event. And the particle ID TXTYTZ is the truth particle data. And the VSVYVZ is the initial data. And pairs, we merge the data in by event and shown it below. The Y is as described before. It is true and false by distinguished particle ID. And here is our features for our exploration for tracking. And DR is the R direction for the pairs data. And DZ is the Z coordinate. D phi is the angle between the particle 1 and particle 2. dr is the d eta 平方 d eta square and d phi square. And z-ling and phi slope is for H classification. And this is our precision data drawn by R and Z coordinates. And the red line is the truth. The blue line is the false by connecting the wrong particle ID. And same as the pairs data, but the data is so large, so I just list a little data. And next.
Okay. This is our purpose for machine learning. We plan to use GNN to classify the truth edge and fake edge. And for GNN architecture, we plan to input the node feature, such as R phi Z, and the edge feature, like d phi, dr, d phi, dz. And we expect to output the weight of each edge. By labeling the output edge, we expect to see the result like this figure. Then we can construct the truth edge. And we try to follow others' project to construct a GNN model, but we haven't finished. Okay, this is it.
Thanks. Questions or comments?
Can you explain again what's the difference between TXTYTZ, VXVYVZ?
I think TXTYTZ is the true position for the particle and hit on the detector. And VSVYVZ is the initial position for the particle.
What does that mean, initial?
Initial.
Why a particle have a true position?
I think it's because the detector has a cross-section, and the cross-section is not precise. So there is, if one particle hits a cross-section in a detector, it will be a distribution, but not a precise position. So it can not be the truth position, I think.
I don't understand your explanation.
Because the detector may be, for example, 5 micron per 5 micron. So if one particle is smaller than 5 micron, so it hits on the detector, the detector will give you a position, but the position may contain a large data in the position by 5 micron per 5 micron.
I still cannot understand. Do you use a TX-TY-TZ VSWB for anything for your study?
Not yet. We are still working on it. We just show the data for XYZ now.
Okay, so I want you to work together with another charge tracking team. All of you
Yes.
can explain to us what is the TX-TY-TZ, TPS-PRTZ, and then what's the difference from VSPRVZ, TS-PRTZ. One thing you can do is that, for example, you can make a plot showing the difference between VS and TX, right? You can make a plot, VX minus TX. You can check the distribution. If that's really what you said, it's about there's some smearing, there's some resolution effect. T is the true position, V is the detected position. If I don't know if that's what your explanation, but you can make some plot to see if that plot consistent with your expectation. It'd be nice
Okay.
to figure out. And also, it sounds like you don't need to use those at all. You eventually you just use a few features to do the study. Is that right?
Yes.
In that case, why do we need those information in the data? It'd be nice if you can explain to us next time.
Oh, okay.
All right. I think we should move on to the next group. So next group is
But so one more comment. So it'd be nice if you can explain to us what is node net, because in your architecture you have HNet and node net. It'd be nice if you can explain to us next time.
Okay.
All right, thanks. So we can move on to group 9, Mr. Chen Junqing and Mr. Chen Lihao.
Wait a minute. I'm trying to share my screen. Can everyone saw my screen?
Yes, we can see your screen.
Okay, so we are group 9, and I'm Chen Junqing. My partner is Chen Lihao, and we are going to talk about the top jet in Large Hadron Collider. So first, I'm going to introduce about the top jet. The top jets are the jets of top quarks or its predicts. And top quark is the most massive fundamental particles and decays in very short time. So it has no time to hadronize and form a jet in most of time. We will detect the top quark as 3 jets in usual, which contains a down quark and a W boson detect as 2 of leptons or other lighter quarks. And in real case such as LHC, we actually cannot record every part of event in collections, since some of the jets has too low energy for us to detect. So there are 2 ways for us to get the data of jets. The first one is the left one, and The first one is to use the CMS detector to detect the energetic jets. It will contain the most part of energy in collections and can get the data for single jets. And the other one is to estimate by the momentum conservation and predict the probability of how many low energy jets there are. Many low energy jets there are, but we cannot get the data for the single jets. So most of case, we get the top jet in TT bar pairs, which usually decays from the high energy gluons. In LHC, since the energy is much more higher than just to form a TT bar pairs, so by conservation of momentum, the top quark will get a large momentum, which makes the top three top jets decay from the top quark looks like just a single jet on detector. We call it get boosted. So how can we distinguish the different events in such many jets and get the right corresponding data for jets? This is our proposal to train the machine learning. So the next part, we are going to introduce our data, and my partner Chen Lihao will give a presentation.
Can everyone see my screen?
Yes.
Okay. I would like to introduce our data. Our data set has 10 files, and each file has over 5 million data. And each data has 3 kinds of features: the high level, low level, and label. The label records what kind of jet of this data. We have 5 kinds of jet, and we have 18 low level features and 53 high level features. And next is the data analysis. Our plan is use this data to classify the jet. The first plan is use the high-level feature to do DNA training. And the next plan is use low-level feature to construct jet image and use this jet image to train CNN. And after we done this, maybe we will try another method like BDT or GNN to do the job. And our DNA structure look like this. We have two hidden layers, and the first has 256 neurons, and the next has 128 neurons. And our activation function is ReLU and softmax. Optimizer is ADA delta. Loss function is categorical cross entropy. And this is our batch size and epoch and validation split. And actually, we have done this part, and this is our result. We only use 1 file in dataset because if we use all 10 files, it will exhaust all memory in Kaggle. So this is the result for only 1 file. And this is the learning curve and hours curve. And this is the confusion metric. And the CN, we will use JPT, JETA, and JPhi to construct J image like this, and use this image, J image, to train CNN. And this is our plan. And okay, this is our reference. Thank you for listening.
Thanks. Any questions or comments?
So, hello. So I think maybe I can comment on the memory issue, and I think there is a lot of students who met this problem in Kaggle's platform, and I would say this is not a problem that make very big issue, because in class you have already learned how to use a generator to input a data into your neural networks. And this is a way to reduce the memory usage. And
Okay.
this is a common way that the competition host in Kaggle and the person who participate in Kaggle competition to train their neural network on Kaggle platform. So if you load all the data once to the memory, it definitely will cause the lack of the memory, because in most of the case, we train on a very large data set which originally have 1 or 100 gigabytes, and after preprocessing maybe become 10 times larger or even more larger. And if you want to find a supercomputer that contains about 1 terabyte memory, that is very hard and very difficult to find. So for a way that to train with a neural network with a small memory, you should use a generator. That is a way to solve the memory issue.
Okay, we will try it.
David, this discussion just remind me, I think it's nice to have a FAQ or tips page, so we can collect the technical issue that we encounter when using Kaggle. Then we have a solution about what's the recommended way to bypass those issues. This would be a very useful thing for long term.
Sure, I think maybe Aaron can try to create a FAQ for this problem.
Right.
Yeah.
And then we can start collecting any experience sharing that everyone feel like useful, and the issue they found, and then the way they resolve it. This would be a nice page.
Okay. I think so.
May I just clarify? So this is a multi-classifier, right?
Yes.
For your study. Okay.
Yes.
So I have one question. So last week, the other group working on TopJet saying that I recall there are 2 variables which look like they're the same. And how does your group deal with that? Do you use that variable, or do you use all the variables in your DNN, or you just select ones that you think it's more powerful? And how about the ones that seem to be duplicated? Have you figured out why?
In DNN training, I use all 53 high-level features. So I didn't.
We didn't find the same features that.
We use all high-level features. Yeah.
So, and then that means you should talk to the other top group team, and 4 of you should figure out how those high-level features are calculated from low-level feature. It'd be nice if you can show us the formula, the definition of a high-level feature in the final report. And from there, you should be able to understand whether the 2 variables they are actually identical.
Okay.
All right. So if no further comments or question, we can move on to the last presentation of the day from Mr. Chen Yuanzhang and Mr. Lu Zhirong.
Let me share my screen. Ah, 怎么办？他没办法 share。好。Sorry that we cannot share our screen from Chrome. It requires the permission. I didn't grant the permission. So.
I think if you have permission, can one of you do that? Otherwise, I'll do that for you.
Lu Zhirong will do that.
Okay. Okay, we can see your slides now.
Okay, we are group 10 formed by Lu Zhirong and Chen Yuanzhang. Our topic will be machine learning on gravitational waves. Okay, let's first talk about the physics. gravitational waves are first predicted by Einstein's theories of general relativity. The equation shown above describes how space-time is bent due to the existence of the massive.
Yuanjia, you probably want to move closer to the microphone because you sound a little bit further away. It's not that clear.
Okay.
That's much better.
The equation describes how space-time is bent due to the existence of massive stellar object. So we can think of space-time as a fabric that bends or curves when we place an object on it, just like the figure shown on the right. But where do the gravitational waves come from? Gravitational waves are produced by masses moving through space-time in special ways. The simplest system that produces gravitational waves in two masses is two masses orbiting their common center of mass. A binary black hole is one simple case. And the first direct gravitational wave signal ever recorded is the BBH G.150-914 signal. So next page. And this graph shows how gravitational waves are generated by BBH. It carries the information of the stellar object. So the observation of gravitational waves actually provides a further means of making astrophysical observations. Now we have a sense of how gravitational waves are generated, but what exactly is being measured by the detector? When we solve the Einstein equation, its nonlinearity makes it really hard to solve, so we must adopt a perturbation approach to linearize the equation. We first assume it's a weak gravitational field. This allows us to decompose the matrix into Minkowski matrix, which is our flat space, plus a small perturbation. And this perturbation is being recorded by the detectors as strain, which represents the fractional amount by which the distance are distorted by the existence of mass. So as the plot reveals, the LIGO data is very closely match Einstein's prediction. Let's have a look at the real data. And, it's an open source data. We downloaded it from the Gravitational Wave Open Science Standard. It's a data detected by LIGO at Livingston in September 14th, 2015. As we investigated into the data, we can see it's a tree-like structure, just like the data we see as the root file we used in class. And from the previous plot shown by LIGO, we kind of get the idea that the data is being recorded as string versus time. So when we investigate into the data, we pull out the most two important components, which is the string and time sequence, and we plot it, and it's shown on the right. We can see the signal is kind of messy, so the classification between signal and noise becomes a big issue when we do the gravitational wave study.
And as we can see, once we extract the waveform from the data, as shown, the data was shown in the previous page. We found that they look similar to the one predicted by general relativity. As shown in this figure, the below shows the waveform predicted by general relativity, and the above was the waveform extracted from the data. However, this data analyzing process always takes lots of time and effort. Thus, we would like to use machine learning skills to accelerate this process. And since there are up to now only approximately 50 binary black hole events detected so far, which are far too less to train a good machine learning model. So we plan to generate simulated data by ourselves. First, we will apply the PyCBC pipeline to generate the waveform as shown in figure A. And second, we simulate the instrument noise of the LIGO detector as shown in figure B. And then, figure B is the sum of the instrument noise and the Gaussian noise of the signal. The sum of the two noise. And finally, we add up the signal and the noise to form to simulate the real data. So our machine learning project is planned to do the classification. So our purpose is very straightforward. We just want to apply machine learning skills to distinguish the detected data, whether it contains a GW signal in it or not. So, and since we found that in these two papers, they generate a similar data with us. And also they apply a CNN model to classify whether a detected data contains a GW signal or not. And they apply similar method to do parameter estimation. So we also plan to do parameter estimations in our study. And these are our references. Thank you for your attention.
Thanks. Any comments or questions?
Thank you. I think this is a good talk. Thank you for preparing, spending effort, making your time for this talk. Can you briefly comment on the difference between your gravitational wave project from the gravitational wave project last week?
So I think the gravitational wave project last week focused on the co-collapse of a supernova signal, and our project is focused on the signal from binary black hole merger. So I think the main difference is that our project is now a detected signal, while the supernova signal has not been detected yet. And the project we would like to do is a classification
sorry, may I
and a parameter
sorry,
estimation.
But I have to interrupt here. So did you sit together with Yuan Zhang next to each other? Because I can hear echo.
Yeah, sorry.
So when maybe one of you can mute when the other person is talking, then there will be no echo. For example, Yuan Zhang,
can you hear me now?
I can hear both of you. There's a huge echo. So is it okay? One of you can
microphone.
Yes, one of you can mute. Okay, then when the other person is talking, now this is much better. Yeah. Okay. So now let me try to summarize what you said. See if I understand you correctly. So first, you correctly explain the source of gravitational wave are different. Okay.
Oh.
And second, because of the source are different, can you comment on difference of the signal waveform between the source last week and the source this week? What's the major difference of the signal waveform?
The waveform from the last week comes from the supernova, so there has been different signal, different shapes.
And what's the shape difference? Is the strength different? Is the duration different?
The strength different. So as you can see, our waveform from the binary black hole merger is more like periodic waves, and then they slowly get much greater, and then they get much smaller later. However, the waveform from the supernova are not this kind of shape.
Okay. And you come another signal difference. And is that the only difference between you two's project? You are dealing with different waveform? Is that the only difference?
And I think that our purpose is also different. So the last week, they tried to make a parameter estimation of one single parameter. I remember it's the angular velocity. And in our group, we plan to do the classification to distinguish the signal from the noise. Also, we try to do the parameter estimation of the parameters. And these parameters, we haven't decided what parameters exactly we are trying to estimate yet.
So you have a classification text and they don't have. And you have a parameter estimate, but they also have a parameter estimate. So the parameter estimate, this part will be the same.
Yes, yes.
Okay. Did the four of you talk together? Because you guys should share similar technology.
Okay.
Xinhong and Yu Hui, did you talk to each other? With Yuan Zhang and Zhilu?
We haven't, but we will be in contact with them later after the meeting.
Yeah, okay, that will be nice. Yeah, I noticed Yuan Zhang and Zhirong, your team seems quite advanced. This is very good. Yeah.
Okay, thanks.
Thanks.
So I think there's another major difference. And last week, there's only signal model, right? Xinhong and Yu Hui did not touch about how the noise look like. But in your project, you also want to embed the noise. So
yeah.
your project will be more complicated.
Oh, yes. That's,
okay.
Just one quick question on your plan. So you mentioned you're going to follow like a couple of references. Do you also plan to use CNN, or you have other machine learning models in mind you want to try out?
Actually, we plan to use CNN and follow the models that listed on the paper, like this too.
Okay, so you also plan to do the parameter estimation on the masses of the binary black hole system?
Yes.
Okay.
Sorry, I think they just do a classifier, right? They did not do PE.
No, the figure C is a PE, and since they only determine the masses of two black holes, so the upper size is also 2.
Okay, got it. So in principle, you can expand this because the model you have probably have 15 parameters, right?
Yes.
Instead of just 2 parameters.
Yeah.
Okay.
Okay, good. So so I think we're done for the presentation for today. And I think we still need to do sign off as last week. TAs can confirm that, right? Like you share, you basically summarize your progress for this week on a shared Kaggle notebook. Maybe one of the TAs can confirm. Is that the plan for today?
Yes. As last week, you can just copy and edit your previous notebook and do something today, and then put some summary in the last cell. And after you finish, you write your summary in the last cell. You can post sign off in the Discord. Yeah.
Thanks, Alan. So, so any questions for what you have to do for today? All right. If not, then I think we can close this Google Meet. And any announcement you want to make, Shijie?
No, I just want to say thanks for everyone. I learned a lot today. Thank you.
Yeah. Thanks a lot, everyone. So, all right, take care, and I'll talk to you next week. Bye.
Bye.